Yeah. Dear students and viewers, today let us discuss about the staggered grid and the simple algorithm, which are very important in the field of computational fluid dynamics. So when we want to discuss about simple algorithm, before going to simple algorithm, it is always better to have a very good knowledge about the staggered grid. Let us see what is meant by staggered grid. So I am drawing the grid lines. So let us see, this node is the present node and this node is my eastern node, this node is my western node, this node is my northern node and this node is my southern node. So we can see the node P is in the center and the eastern node is here, the northern node is here, western node and southern nodes are here. So these are the grid points, and the control volume of the present node P will be given like this, is given like this. So this is the control volume which is encompassing the central node P. To the eastern side face it is E and to the western side face it is small w. Always it is a general convention to use small letters for the faces and capital letters for the nodes. So now this control volume P has the eastern face as E, western face as W and the northern face as N and the southern face as S. If I am going to consider 2D. Similarly the same can be considered for a 3D also. Now we have taken a two-dimensional grid domain. Now why you want to go for staggered grid, or what is meant by staggered grid, is that generally any value like your pressure, temperature, density, these are called as scalar variables, and your vector variables are u, v, w. There are some more scalar and vector variables also, but the main concerns are, these are the important terms which are related to the field of computational fluid dynamics. These are the primitive variables, and hence we want to know the value of pressure, temperature, density, the components of velocity u, v and w. Here all these values, both the scalar values and the vector values, are generally stored at the center of the cell. So if I am going to consider the P as my control volume encompassing my eastern side face small e and the western side small w, and similarly the northern and southern face, this volume what I have indicated in the shaded line indicates that all these values will be stored at the center of the cell. So all these values will be stored at this point. So all these values, namely the pressure, temperature, density, u, v and w, are stored at the center point. This type of arrangement is called as collocated grid or co-located grid. We can call in two ways. It can be called as collocated grid or co-located grid. What is co-located? Both scalar variables and vector variables are co-located. They have been located in the same location. Okay, so this is nothing but co-located grid. Or what is the limitation of this co-located grid? Why you want to go for the staggered grid? That is what we are going to see right now. Okay. So let me take the x momentum equation or the u momentum equation, which is given by dou rho u by dou t plus dou by dou x of rho u squared plus dou by dou y of rho u v plus dou by dou z of rho u w is equal to minus dou p by dou x plus dou by dou x of tau xx plus dou by dou y of tau xy plus dou by dou z of tau xz plus rho into fx. So this equation is nothing but called as the Navier-Stokes equation or the U momentum equation. This equation, before going to deep into this equation, these equations are generally called as transport equation. So we can say the continuity equation, momentum equation and energy equations are generally called as transport equation. So some property is being transported. Here the momentum is transported. Okay. So here we can see the first term is generally called as transient term. The first term is generally called as transient term. Any guess why I am using this term as transient? Any idea? Yes, is right. Because in the denominator we have dou t. Here the t indicates time. So any variable which is going to vary with respect to time is known as transient condition. If it doesn't vary with the time means it's called a steady state. But he is here he is going to vary with respect to time means it's transient. So we are giving importance to this denominator term dou t, and hence the first term is called as the transient term. And the next three terms, these terms are called as convection terms. The next three terms are called as what? Convection terms. What is the idea behind convection? Whenever you have a term with u, v or w, the velocity components, then that particular term is called as convection term. So we have here u squared, here we have uv, here we have uw. So it's been the property has been transported by means of convection. The property is transported by means of convection. Then there may be a query for you. Sir, here is also there is a u term. Here also there is a u term. Even the u term is there, but we are giving more importance to the time, and hence it is called as transient. Here you can see there is no time term involved, and hence we are calling these three terms as convection terms. And coming to the right hand side terms, these three terms are called as diffusion terms. These three terms are called as what? Diffusion terms. Why means all these terms will definitely contain a term called as the diffusion coefficient. In this case, if I want to write tau xy, it will be mu of dou by dou x plus dou by dou y. When I want to write here is y, so I have to put as v. Here it is x, so I have to put as what? U. So we can see this tau xy term has a diffusion coefficient. That diffusion coefficient is nothing but your mu. Is nothing but what? Coefficient of dynamic viscosity. Similarly, if I want to write tau xz, it will be mu of, how to write? X and z are there. So you write dou by dou x plus dou by dou z. Yeah, that's right, because we have to give for both the term x and z. Since z is there, the corresponding velocity component is w. Since x is there, the corresponding velocity component is u. So we can see in all these diffusion terms, even if we are going to take tau xs, there will be a term ending with mu. So these are the terms which have diffusion coefficient, and hence these three terms are called as diffusion terms. And generally this term is called as pressure term. Sometimes we can take it as a part of the source term also. Definitely this is nothing but what? Your source term. Definitely this is nothing but our source term. This term rho into Fx indicates the body force. Indicates the body force. So I will repeat once again. We have taken a big equation and trying to explore the various terms involved in this equation. So if you want to put, I can put a, I'm sorry, we have to take up to here. Yeah. So we can see here dou by dou t of rho u plus dou by dou x of rho u squared plus dou by dou y of rho u v plus dou by dou z of rho u w is equal to minus dou p by dou x plus dou by dou x of tau xx plus dou by dou y of tau xy plus dou by dou z of tau xz plus rho into fx. So this equation can be broadly classified into various terms as transient terms, convection terms, diffusion terms and source terms. Whenever there is a term with the time derivative, it is called as transient term, and whenever there is a term with u, v or w, they are being conjected and hence they are called as convection terms. And coming to the right hand side, we can see the three terms with tau x-axis, tau xy and tau xz has diffusion coefficient term, namely mu, and hence they are called as diffusion terms. The other two terms are generally called as source terms. Surely the rho into fx is called a source term, and even we call this minus dou p by dou x as a pressure term. Is nothing but a pressure gradient term. We used to call as the pressure term. So generally any transport equation will be of the form T plus C equal to D plus S. Any transport equation will be of the form T plus C equal to D plus S, which means transient terms plus convection terms will be equal to the diffusion terms plus source terms. So I hope now we got an idea about the x momentum equation with the various terms involved. Let us now try to explore about the continuity equation. Dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equal to 0. Here also, what is the first term? Can you tell me? What is the first term? Very good. It is transient term. Why it is transient? Because we have the time derivative. What about the next three terms? Which terms are involved there? U, V and W. So definitely they are convection terms. Convection terms. So we can see this continuity equation what we have taken is of the form T plus C equal to 0. There is no term involving D or there is no term involving S. That is, there is no diffusion term, there is no source term. So I hope you could understand that any transport equation is of the form T plus C equal to D plus S. All the terms need not to be there. It can be of this general form. You can put into any form of this one, where here D and S are set to be 0 for this continuity equation. Let me try to write the V momentum equation. So the V momentum equation will be dou rho V by dou t. So this is a transient term plus dou by dou x of rho u v plus dou by dou y of rho v squared plus dou by dou z of rho v w is equal to minus dou p by dou y plus dou by dou x of tau xy plus dou by dou y of tau yy plus dou by dou z of tau yz plus rho into fy. So now you know the answer very easily. This is a transient term. These three terms are my convection terms. These three terms are my diffusion terms. The other two terms are source terms, especially this dou p by dou y is called as the pressure gradient term. Because of pressure difference only the flow will happen. Okay, so based on that only we are able to have the flow. So now you know about U momentum, V momentum. Similarly, you can write the expression for W momentum equation. Also you can write the expression for energy equation. That can also be fixed in terms of what? Transient plus convection equal to diffusion plus source. So this is a general knowledge, this is a generic knowledge which is required before we are going to staggered grid. So I am coming back to staggered grid now. So now the idea is that we are trying to store the scalar and vectors, namely the pressure, temperature, density, these scalars, as well as the elastic components of the, namely the U, V and W, are stored in the center of the cell. It is going to be get stored in the center of the cell. Now I am going to take a arrangement called as checkerboard arrangement. I will explain you what is meant by checkerboard arrangement. The checkerboard arrangement is similar to that of a chessboard, or there is a board also called as checkerboard. Both are one and same. Both have 64 squares and alternately black and white. Why this term checkerboard is used, I will try to explain you. So this is nothing but checkerboard arrangement. So I will try to have number of grids. Yeah, I will take this as my present node, and this is my west node, this is my eastern node, and let us say this value here is 100, this value is here 50, this value is 100. The pressure values at P is 50, the pressure value at E is 100. Similarly, at the northern node is once again 100, the southern node once again it's 100. If I am going to have another node, for example, if I am going to extend this one, so this node is called as EE, that is the node eastern side of the E node is called as EE, that is once again 50. So you can now see the alternate arrangement. The first value is 50, then is first value is 100, the second value is 50, then once again 100, once again 50. So it is alternate black and white, or alternate white and black. So the value is going to get repeated in this fashion, is called as checkerboard arrangement. Is called as what? Checkerboard arrangement. So if you want to extend this side also, I can extend it. Just for your understanding, first of all we should know what is meant by checkerboard arrangement. Okay, so still one more line. Yeah, so this node is called as my WW. So definitely what will be the value here? Here it is 100, means what is the value left to W? It will be 50. So we can see the values are getting alternately, like 50, 100, 50, 100, 50. Similarly in the word action also. Similarly in the word action I do not take much time. So I hope you got the logic. So it's 50, 100. The next value here will be what? Once again 50. Similarly the next value here will be what? Once again 50. So this type of arrangement of the values alternatively appearing is called as checkerboard arrangement. Now let us say these values are nothing but the pressure values. So the value of the pressure is stored for the present node P at the cell center, namely 50. Similarly, the value of the pressure for the node E is stored as 100 in the cell center. Similarly, the value of the pressure at the node W is stored in the cell center of this particular node as 100. So if it's such a case, how to evaluate the pressure gradient, namely the dou P by dou X? How to evaluate the pressure gradient? Now the dou P by dou X. So what about the grid arrangement here? This is my control volume. This is nothing but my control volume for the present node, which is encompassed by my eastern phase as E, my western phase as W, northern phase as N, and southern phase as S. So I have the value here as 50. That's fine. Now let us try to find out the value of minus dou P by dou X. Where this minus dou P by dou X is coming? It is coming in the U momentum equation. I will just show you where it is. Yeah, you can see this term is there. You can see this dou P by dou X is appearing on the right hand side of the U momentum equation. So I want to calculate what is the value of minus dou P by dou X. As I told you already, this gradient in pressure will drive the flow. Whenever there is a pressure difference, then only the flow can happen. If the pressure is same, then there is no flow at all. So that we know already. That is from the basic concept of fluid mechanics. That's fine. Now let us try to find the value of dou P by dou X, and I am going to apply this finite volume method. So when I am going to go for finite volume method, I want to integrate with respect to triple volume, because I am going to consider this as a three-dimensional flow. So I am going to make, yes, I am going to make it as minus or in triple integral of, even you can take inside my or outside, nothing wrong in that, minus dou P by dou X of dx dy dz. So I am going to integrate minus dou P by dou X with respect to dx dy dyz. Okay, because the control volume. When I am going to integrate dou P by dou X, it become P. It become what? Because the first derivative will become the normal value. If I am going to integrate P once again, it will become P squared by 2. But since I have already the first derivative dou P by dou X from basic integral calculus, we know that when I am going to integrate dou P by dou X with respect to dx, I will end up with P. Okay, so the value is minus P, because the minus sign is already there. from the limits from where to where. I am going to start from W and I am going to end at E. That is my limit of integration. Okay, so it is W to E. What will happen to dy? Dy will become y. When I am going to integrate dy, it will become y. But my control volume is very small. So y is nothing but my delta y. Why I am putting inside of y delta y? Because my volume or the length corresponding to y direction is very small or a small control volume, and hence y is considered to be delta y. Similarly, when I am going to integrate dz, I will end up with z. But once again, as we know, the control volume is very small. We are assuming that the size of the dimension in z direction is also minimum, and hence it is called as del y del z. Okay, so it is, otherwise I can put like this, minus p of w to e. This del y del z can be called as area. This is nothing but what? The area. Okay, because you know length into breadth is nothing but your area of this cell. Okay, now I am going to apply the limits of integration. So it will become minus PE minus of minus PW into area. So I am just trying to apply the limits. This minus sign is coming because of upper limit minus lower limit. This is because already the formula has minus P. So I hope you got it. So it is minus PE, minus of minus will become plus PW into A. Now the question is whether you know the pressure value at this eastern face. No, we are not aware of the value at the face. We know only the values at the nodal points, namely P, E, N, capital S and capital W. But we do not know the value at the faces. So we are not known about PE and PW. I will take it to the next page, or before going to the next page, it is better to have here itself what is PE or how to find PE, because we are not knowing the value at E. So definitely we assume it is a central diffusion. So it will become, or we can take the linear interpolation. So it will become PE plus PP by 2. The average value between these two will be the value at here, here. Okay, that is the idea. So because we do not know the value at the face, but still we want to know the value at E. So we are going to take the linear interpolation between the two nodes where we know the value, Similarly, can you now help me with the PW? What is the value at this face? Not a point, it's at the face. What is the PW? Yeah, you are right. So it is PP plus PW by 2. That is, take the pressure value here, take the average of them. So now you know what is PE, you know what is PW. So let us move on to the next slide. This can also be written like this. Instead of minus PE plus PW, we can write as PW minus PE. Both are right. Into A, into nothing but our area. Let us move on to the next slide. So it is, what is P? It is P small w minus P small e into area. So what is PW? Right now we have obtained the value of PW, which is nothing but what? The average value of PP and PW by 2. These are capital letters, this is small letter. So we are trying to convert the value from the face to the nodes. I hope you got it. Minus, what is the value of E, PE? So it will be PP plus PE by 2. So you don't forget to put the bracket, PP plus PE by 2 of area. Now we can take the LCM, it will be 2, it will be PW plus PP minus PP minus PE of area. So what will happen? This PP get cancelled. Now what is the answer? It is PW minus PE by 2 into area. Now do you know the value at PW? Yes, we know. Why? Because they are the nodes. Capital W indicates the nodes. Similarly, what is PE? We know the value because of the nodes. Okay, let us go back. What is the value of PW? 100. What is the value of PE? 100. Got it? What I am telling? The value of PW the value of PW is 100. The value of P is also what? 100. So with this knowledge, we will go to the next slide. So it is 100 minus 100 by 2 into area. The answer is 0. The answer is what? 0. Which means there is no pressure gradient at all. When there is no pressure gradient, the flow cannot happen. The flow cannot happen. But whether we are able to predict the real time physics, no. But there is a pressure difference actually. Why there is a pressure difference actually? Because it moves from node to node only. 50 to 100 or 100 to 50. It is happening what? There is a pressure difference of 50 Pascal or some values. So this is not equal to 0. So there is a pressure gradient is there. But with our approach, what we have ended up here, it is not reflecting the real physics. It is giving some other physics which is not realistic. So we are not able to capture the real physics, which means there is some problem in storing our values at the cell center. I will repeat the statement. When we are trying to find out the value of dou P by dou X, we ended with the value as 0. 0 means there is no pressure gradient. There is no pressure gradient, which means the flow cannot happen. But in the real time physics, the flow will happen either from left to right or right to left. The flow will happen because of pressure gradient. Since in this method we are not able to capture the real physics, we are trying to explore why we are not able to capture the real physics. That may be due to because we are storing both the scalar variable and the vector variables in the same cell center. In the same cell center. If it is going to be get staggered, then we can overcome this problem. So what is the problem they have identified is that we should not store all the variables, namely the pressure, temperature, density, these scalars along with the vectors u, v, w in the same location. The same location means what? On the same cell center. So now we are going to stagger it. Now we are going to move little further. Which one we are going to move little further? This vector quantities will move further. Little bit we will move. Then we will see whether we are able to overcome this problem. Yes. Let us try now. What I am going to do means, I am going to move this control volume encompassing the eastern phase and western phase. I am going to move it towards the right for the U control volume. So now the U control, earlier the control volume is common to everyone. Now we are going to separate the scalar control volume or the main control volume and the velocity control volume, U control volume and V control volume. We are going to define as what? U control volume and V control volume. Okay. If I am going to draw, you can understand. Now I am going to stagger it. I am going to move it. Okay. So I can see. Now whatever I am indicating in my red color is nothing but my U control volume. Is nothing but what? U control volume. Earlier my main control volume is on the left hand side, whereas my U control volume is slightly shifted to the right hand side. So this is nothing but called as my UE. Is nothing but called as what? UE. So this U control volume is moved to the right. Now what are the endpoints of this U control volume? The node P and E. The node what? P and E. Now we can see I am going to move the V control volume towards the y direction. Since I am moving the x velocity or the u velocity along the x direction, I am going to move the v velocity along the y direction. That I can show here as in green color. I can show you. Okay, I am going to move it little up. So it will be like this. So whatever I have drawn in green color is nothing but my V control volume. So generally that will be indicated as small vn. So now this small control volume V has the n limits as what? N and P, capital N and P. So we have staggered the vector control volumes to the right and to the top. And the main control volume or the scalar control volume is there itself. We are not moving it. Whereas the velocity vector components or the velocity things are moved to the right and to the top. So now we have how many control volumes? There are 3 control volumes. What are they? The first one is nothing but my, or I will write the last one, V control volume. Then whatever I am showing in red color is nothing but my U control volume. If it is going to be 3 dimensional, there will be W control volume also, but it is easy to understand the concept with the 2D, and hence we have restricted ourselves to U control volume and V control volume. What is the one more control volume? Yes, you are right. The one more control volume is what? The P control volume or the main control volume. So what is the advantage of staggering it, the control volumes? Let us see now. So now the U control volume starts from P and ends at E. The V control volume starts at P and ends at N. This is the idea. So what is the value at P? The value at P is we have shown here. Yeah, the value at P is what? 50. The value at E is what? 100. Okay. So we have to understand the control volume very clearly. The control volume starts from P and ends at E. The value of P is 50, the value of E is 100. That's what I want to communicate to you. Otherwise, I will write it here itself. So we can see the value of pressure at P is 50, the value of pressure at E is what? 100. The red color indicates from here, this entire thing is nothing but my U control volume. Whatever I am going to sketch is nothing but my U control volume. I hope it is more clear now. So it starts from P, ends at E with the vector UE along the center point, This is my E, this is nothing but my E. I will take this control volume alone and draw separately, and once again we will try to find the value of dou P by dou X, and once again we will try to find the value of dou P by dou X. Yes. Any doubts so far? Okay, fine. So now once again I am drawing this U control volume. The U control volume is like this. It is here P, here it is E, and here it is E, and the velocity wave along this one is UE. Okay, UE. So what is the value of the pressure at P? It is 50. What is the value of pressure at E? It is say 100. Now once again I am going to repeat the same steps. What are the same steps? I want to find the value of dou P by dou X. Okay. So the value of dou P by dou X is what? It is minus dou P by dou X. Where this term dou P by dou X is coming? Once again I want to recall the basic. Where this dou P by dou X is coming? Whether it is coming in the kinetic equation? No. Whether it is coming in the V momentum equation? No. It is coming in the X momentum equation or the U momentum equation, and hence I have taken the U control volume. I hope I have made it very clear. I will once again repeat it. This term dou P minus dou P by dou X is there in the governing equation of U momentum equation. It is not in the either V momentum equation or W momentum equation or the kinetic equation, and hence I have to take the U control volume, and hence I have taken here the U control volume. So it is minus dou P by dou X. Once again I am going to do the integration, because based on the finite volume method. So it is minus triple integral of dou P by dou X into dx dy dz. As I told you earlier, when I am going to have the integration for the first derivative, it will be the same variable minus P. Now you see the limits. What are the limits? You see the screen, and what is the limit? It is from capital P to capital E. Earlier it was different. Earlier the limits were different. Now the limits are different because we have staggered it. So we want to move from P to E. We want to move from what? P to E. Of when I am going to integrate dy, it becomes delta y. I have already told the reason. Similarly, dz will become delta z. So now what happens? You see, I am going to apply the limits minus Pe minus of minus Pp of del y. Del y del z is nothing but area. Del by del is nothing but what? Area of this control volume. Control volume is nothing but what? U control volume. So I can keep it as AE. If you are not happy with AE, he can read it with A itself. Nothing wrong in that. So now it will become capital PP minus PE of AE of AE. So we can see what is the value of PP now? It is 50. What is the value of EPE now? Is 100. So whether it's equal to 0? No, definitely it has some values, whether it's positive or negative, adverse pressure gradient or favorable pressure gradient. In some way the flow will happen according to the pressure difference, and hence we are able to what? Obtain the real time physics happening. Yearly with the collocated grid we found that we are unable to predict the proper value of dou P by dou X because all the control volumes are at the same location. But when I am staggering the U control volume to the right hand side, I am able to predict the value of dou P by dou X more exactly. Similarly, if I am going to stagger the V control volume, I will be in a position to find the value of dou P by dou Y more realistic. That is the reason why we are moving from the co-located grid to the staggered grid. Now this staggered grid will helpful in solving some problems like checkerboard arrangement. We are not telling always the pressure value should be 50, 100, 50, 100. If there is a certain case like this, then whether our collocated grid is able to solve the problem means it is unable to resolve it. So we are trying to get the help from the staggered grid. Okay, so I hope you got the logic of understanding what is the use of the staggered grid in finding the pressure gradient terms, mainly the dou P by dou X here. That is, we are able to have the real time, we are able to capture the real time physics. With the collocated grid we are unable to do it. There are some limitations, but nowadays there are some more technologies have developed where we are able to solve with the help of collocated grid also. That is not our concern today. Our concern is to know about the staggered grid. What are the advantage of staggering the U control volume from the main control volume? What are the advantage of staggering or moving the V control volume from the main control volume? That what we have seen, and I hope you understood the concepts. So now we have completed the staggered grid arrangements. Let us move further for the simple algorithm. Are you okay with this? So once you are very confident with this staggered grid arrangements and the control volumes, let us move further for the understanding the simple algorithm. The term simple stands for semi implicit pressure linked equations. So that is the meaning of the simple semi implicit pressure linked equations. This is mostly applicable or needed for incompressible flows. A flow in which the density remains constant is known as incompressible flows, or the density cannot vary. And one more thing is, this simple algorithm can be applied to 3D. There are other functions like stream vorticity functions which can be applied only for 2-dimensional, where the simple algorithm, the real advantage is that we can apply for a 3D domain, 3-dimensional domain. Okay, what is the meaning of 3D means? It's 3-dimensional domain. Okay, fine. Then it is applicable for the real fluid. So if it is a real fluid means what is the another fluid? It is called as ideal fluid. Ideal fluid is a fluid which do not have viscosity, whereas the real fluid is a fluid which has or which possesses viscosity. So these are the various conditions, first of all, we are trying to know before entering into simple algorithm. The first point is that it is applicable for mostly for the incompressible fluids, that is when the density remains constant. The second thing is it is more suitable for the 3-dimensional geometry. Even it can be reduced to 2D and 1D, but the advantage is we can extend it to up to 3-dimensional domain. The third one is it is applicable for the real fluid, not for the ideal fluid. If you are going for the ideal fluid, then the equation will become what? Euler's equation. Then the ground equations will become Euler's equation. Yeah. If it is going to be a real fluid, then we will call the corresponding momentum equations as Navier-Stokes equation. One person is Navier is a French military engineer, and the another person Stokes is a English mathematician. Both have developed this momentum equation separately at two different locations during 1850s, mid of 1850s, and hence in order to recognize both of them, we have given the name as a Navier-Stokes equation, generally called as NSE. This is applicable for the real fluid. Okay, now let us move further. Why this simple algorithm is required? Why this simple algorithm is required? That is what we want to know. So first I will write the continuity equation. I will write in small font because I want to accommodate all the equation, namely the continuity and the three momentum equations. Okay, dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y plus dou by dou z of rho w is equal to 0. This equation is called as the continuity equation, arrived from the conservation of mass. He says that m dot 1 will be equal to m dot 2, that is mass is conserved. So continuity equation means mass is conserved. The second thing is the u momentum equation, the third is the v momentum equation. So already we have seen this one, so I will write fastly. Dou by dou t of rho u plus dou by dou x of rho u squared plus dou by dou y of rho u v plus dou by dou z of rho u w is equal to minus dou p by dou x plus dou by dou x of tau xx plus dou by dou y of tau xy plus dou by dou z of tau xz plus rho into fx. Equation number 2. Equation number 2 is nothing but u momentum equation. It is arrived from the fact of Newton's second law of motion, F equal to ma, where the forces are conserved, or indirectly, since it is in motion, we can tell the momentum is conserved. Similarly, coming to the v momentum equation, it is dou by dou t of rho v plus dou by dou x of rho u v plus dou by dou y of rho v squared plus dou by dou z of rho v w is equal to minus dou p by dou y plus dou by dou x of tau xy plus dou by dou y of tau yy plus dou by dou z of tau yz plus rho into Fy, where rho into Fy is the body force along the y direction. This equation number 3 is known as v momentum equation. Similarly, I can write the w momentum equation also. So it is dou by dou t of rho w plus dou by dou x of rho u w plus dou by dou y of rho v w plus dou by dou z of rho w squared is equal to minus dou p by dou z plus dou by dou x of tau xz plus dou by dou y of tau yz plus dou by dou z of tau zz plus rho into fz. Equation number 4, which is nothing but called as my W momentum equation. Okay, so now I have written the governing equations for the conservation of mass and the conservation of momentum along the x, y and z. So what is our objective? What do you want to find from these equations? What do you want to know from these equations? Let us say the flow is incompressible, or the fluid is incompressible. The fluid is incompressible means rho is no more a variable, is going to be a constant. So rho is going to be a constant. So now from these four equations, what is your intention, or what is our intention? Our intention is to find, because rho is already known, because a constant is not going to vary. We know the type of fluid and it is not going to vary. So here the variables are u, v, w and what is the one more variable? You can see here u is there. I can indicate in another color. So u variable is there, v is there, w is there. Okay. What is the one more variable? What is the one more variable? Yeah, you are right. The one more variable is my pressure. So there are how many variables? There are 4 variables. How many equations? There are 4 equations. If I am going to join continuity, then there are 4 equations. So we may think that the closure is been satisfied. There are 4 equations, 4 unknowns. We can solve it and easily get the value of u, v, w and p. But it's not quite simple like that. It's not quite simple like this. Why means? Because these continuity, I will omit continuity now. I will have only momentum. Let us see. Let us, for example, for instance, let us forget about the kinetic equation. Let us have only the momentum equation. So in the momentum equation, there are 3 equations, there are 4 unknowns. If I am going to consider only the momentum equation, there are 3 equations, but there are 4 unknowns, namely u, v, w and p. So whether it is possible to solve 4 variables from 3 equations? No, it is not possible. So we are trying to make use of the kinetic equation also. Okay, now there are 4 equations and 4 unknowns, but still it is not so easy to find u, v, w and p. Why? Because here there is a term called as pressure term, which is available in the momentum equation, which is not there in the kinetic equation. In the kinetic equation we have only u, v and w, and there is no term called as pressure term. So but how we are going to have a connection between this momentum equation and the kinetic equation then? That is called as pressure linked equation. How I am going to link the pressure to my kinetic equation is called as pressure linked equation. So I am coming to the topic. What is the topic? Simple semi implicit pressure linked equation. So now I am explaining how we are going to link the pressure term to the kinetic equation. That algorithm is called as simple algorithm. So if I am going to some way going to relate or link my pressure term from the momentum equation to the kinetic equation, then my problem is solved. That algorithm is called as simple algorithm. In another 10 to 15 minutes, we will try to know what is meant by semi implicit. Now we got the logic of pressure linked equation, but we do not got the logic of which one, especially the semi implicit. That let us try to explore. So now I hope you got the logic for what we are going for simple algorithm. The logic for simple algorithm is that it is for the incompressible fluid, which means the density is constant. We are trying to make use of the kinetic equation and momentum equation to find u, v, w and p. There are 4 variables and 4 equations, but it is not straightforward to get the answer directly because the pressure term is missing in the kinetic. So how I am going to link the pressure term from the momentum equation to the kinetic equation? That algorithm is nothing but my simple algorithm.